Hi, I'm John Souders. I'm the Director of Curriculum at the National Center for Optics and Photonics Education, also known as OP-TEC. I want to show you a very interesting byproduct of refraction, which is called total internal reflection. It's a concept that's covered in your Fundamentals of Light and Laser Text, and I want to use applet number 67, which is referenced in your textbook, to demonstrate this particular principle. What you see on the screen is applet number 67. There's a different condition here that you probably already noticed, and that is that we now have the wave of light incident in a medium that has a higher index of refraction than the medium in which the refracted wave moves. So we have always had the wave moving from typically air into water. Now what we have is it moving from water into air. That is, from a high index of refraction to a lower index of refraction. When this occurs, there is this phenomenon of total internal reflection that can result. If I take the slider bar and I begin to move it, nothing really changes from what you've seen in the past. We still have a change in the angle of incidence that creates an angle of refraction up here according to Snell's law. But now if I go to a certain angle, 48 degrees, look what's occurred. We now have the incident ray approaching the surface and getting to the surface and now being refracted at exactly 90 degrees along the surface between these two media. But what would happen to the ray if I go ahead and further increase that angle of incidence? Now you see what we get is total internal reflection. Instead of the ray that is in the second medium, that is air, being refracted, it now is totally internally reflected back into the original medium of water where it started. This is a very important concept in photonics. It is the basis by which we use fiber optics, and we're able to transmit signals with data on them through fiber optics cables and to keep the signal inside the cable itself. I want to conclude this tutorial by showing you how to calculate the critical angle. Because once you can calculate the critical angle, then you know any angle greater than that will be what causes this effect called total internal reflection. Let me get your attention here to these two diagrams that I have up on this whiteboard. This is the condition for the critical angle. You have a ray of light that is coming from the incident surface, which back from the applet we'll recall was water. It now gets to the surface, and because it is at the critical angle, we see that it refracts 90 degrees and goes along the axis here between the two surfaces. Now, in this diagram, you'll notice that here's the critical angle again, as we had right here, and any angle that's greater than that, as you can see from this diagram, will now cause total internal reflection to occur. So this is a very key concept to be able to calculate this parameter, because then it gives you a range of other angles in which total internal reflection will occur. To determine the right formula for doing this, we're going to start with Snell's law, because Snell's law really is the law of refraction, and all the physics that we need for calculating that is built within this equation. I'm going to go ahead and slightly modify this equation to make it a little easier to talk to. Since we're talking about an incident medium of water up here, this is the index of refraction of the water. This is times the sine, and now I want to know specifically what it takes to get a critical angle between these two media up here. So this now becomes the critical angle, replaced from just the general angle of I in Snell's law. And this is now equal to the index of refraction of the refracted medium, which we know to be air. So this is just N of A, which is air. And that's multiplied by the sine of the refracted angle. Once again, since it's now at the critical angle, I know what the measure of that angle is. It's 90 degrees. So I'm going to put 90 degrees in here. And I know that the sine of 90 degrees is equal to 1. So now I have the equation that the index refraction of water times the sine of the critical angle is equal to the index of refraction of the air. Simple algebra will say that then the sine of the critical angle is equal to the index of refraction of air divided by the index of refraction of water. And now what I've got to do is isolate that variable, which is the critical angle, so I can solve for it. And I now have that the critical angle is equal to the inverse sine of the index refraction of air divided by the index of refraction of water. So this now is our key equation. We can plug some numbers in to check this from what we did in Applet 67. You recall there that the critical angle is equal to the sine, inverse sine, and the index of refraction of the air was 1.00, and the index of refraction of water was 1.333. If you take your calculator out, and if you divide 1 by 1.33, and then take the inverse sine of that number, you will find that the critical angle is 48.59 degrees. And as you will recall, as I was playing with that little slide bar, just as we came right at 48, we saw the total internal reflection take place. So we can see that this calculation is accurate. I hope that this mini tutorial has been useful to you, that you now better understand the concept of total internal reflection, and I wish you the very best for the remainder of the course.